Welcome to Calculus BC. In today's episode, we're going to be discussing Chapter 9.1, which is an introduction into sequences, which is a bit of a departure considering where we came from. We just came from logistic growth, but sequences and series actually shows up a lot on the AP exam, and there is calculus involved. And so here we are. This is, I believe this is considered the C part of the Calculus BC. The B part was just the finishing up of the integral, so here we are into sequences and series. So a sequence is defined as a pattern of numbers that are discrete, not continuous, right? So they're not like functions, and they grow or shrink in a specified pattern. I know that's off screen, but I'll move that right there. So here we go. They grow and shrink in a specified pattern. And so in order to compare the two, and of course, the basic idea here is that they are discrete values, they're not continuous values. So if I was to compare two sequences that seem very similar, it would be these guys. So if I did like a sub n equals e to the n versus y equals e to the x, this is obviously a continuous function, right? And so the graph of this would look like your standard e to the x function. It would look like that, right? Where this would be, say, 1, this would be, say, 2, and this would be, say, 3. And then, but a sub n equals e to the n would be a little different. It would start maybe like right here, and it would do one of these maneuvers. Now, notice how the growth pattern is exactly the same, except the points are not connected, and the reason why is in a sequence we only plug in whole numbers, right? So only positives, right? Notice how it doesn't even go into the negative region, but the growth pattern is still the same. Now, oftentimes you will see me compare a sequence to a function, or even like a series to a function, but that's mostly because we want to, when we compare the two, we're trying to see how the growth patterns are similar. And there are frequent times when comparing a sequence to a function is actually quite useful and is going to be necessary for us. But it is important to note that the stark difference between them is that one is continuous and one is discrete. The types of numbers you can plug into a function are going to be any number, right? Depending on its domain. I can plug in, decimals, fractions, all that stuff. I can plug in irrational numbers. But again, when it comes to a sequence, I can only plug in those whole positive numbers. And so make sure we keep that in mind. At this point, up through integrated 3, you will have learned two types of sequences. And so the two sequences that we already know two types of sequences. And if you want, you can go and pause and see if you can recall what those sequences are. But if you are done pausing, then you will know the first one is arithmetic. And the arithmetic sequence is a sequence in which the next term is obtained by either adding or subtracting by a constant, we call it a distance. And so from here, an example of this would be 4, 7, 10, 13. In this case, we know that the distance would be 3. A sub 1, in other words, the first term in the sequence would be 4. And so if we wanted to write an explicit function for this, we could say a sub n, which is the nth term in the sequence, any term in the sequence, would be the first term, which is 4. And then we would add the distance to it, so 4 plus 3, and we always have to take the term beforehand. Now, this is the version of the sequence that you learned in integrated 3, but in integrated 1, you guys actually learned a different version of it, where you would say t of n is equal to, you could have seen the distance as your slope. So the t of n version is very much like mx plus y equals mx plus b, where you have, say, 3n, and then you add the 0th term to it. So to go to the 0th term, I'd go 1 back, so I get 1, so 3n plus 1. Now, what's funny is that if you look at these right now, they look very different, but if you actually distributed the 3 and combined like terms, you'd find that they are the exact same thing. If we were to equate this back to functions, so here I go, right? I'm already equating these to functions. This would be akin to point slope form of a line. This would be akin to slope intercept form of a line. So integrated 1 kind of emphasized the slope intercept version of it, just because we were used to seeing that mostly. So there's your arithmetic sequence, pretty generic, and it's good to know because it does show up sometimes here in sequences and series, not as explicitly as that, but it'll be a piece of a larger sequence. The other one that's actually going to show up more often is going to be the geometric sequence. The geometric sequence is it's very much like the arithmetic sequence, but not, where it's going to be a sequence in which the next term is obtained by multiplying or dividing by a constant, what we call a ratio. Now when I say dividing, we really don't actually divide anything. What we do is we end up multiplying by something's reciprocal to make the value shrink, and you'll see that happen in the very first example here, where if I give you something like 1, and then we go, actually let's make him 1/3, and then I'll make him -1/9, 1/27, and -1/81. These are all separated by commas. The ratio here that's constantly being multiplied each time is going to be -1/3, and my a sub 1 is going to literally be 1/3. So in the geometric formula, we could say that this is going to be 1/3, which is my first term, times -1/3 raised to the n minus 1. And of course, the integrated 1 version of this was actually, it was going to be the ratio, so that they called it the multiplier in integrated 1, and that was just simply raised to the n. And then from here you would put down the 0th term, so that would be 1 in this case, right? Because if you're multiplying by -1/3 to get here, then you would divide by -1/3, making this actually -1 right here. Now, if only life was that simple, right? If only all we had to deal with was geometric and arithmetic sequences, then there would be no need for the thing that we're learning right now. But in Calculus BC, we encounter sequences that are not arithmetic nor geometric. So sometimes it helps to be able to just construct a pattern, and we're going to need to do this quite often, especially when it comes to finding out the general term of a particular series. It's going to be quite useful. So let's talk about how to generate a sequence, how to create a sequence generator. And so this next one here is not going to be very clear as to what it's going to be in terms of what the explicit function is, but we can probably figure out what the pattern is. So if we look at 1/3, -2/5, 3/7, -4/9, and then ... right? So if you look at it, it looks like there's a pattern involved, right? I mean, it looks like, there should be some semblance of a pattern, but it might be hard to tell like what that pattern is. And so you just want to identify the things that you know in this thing. So what do we know about this? Well, we know that it's alternating. And what I mean by that is it's going from plus to minus between each term. So it behaves very much like a geometric sequence here in that vein. And whenever you're dealing with a fraction and you can't really tell how it's growing, try to look at the top and the bottom individually and see what's going on here. So the top, or the numerator, well, what's going on there? Well, if I was to call these out by their index value, in other words, if this was going to be the a sub 1 term, and this is going to be the a sub 2 term, a sub 3, and a sub 4, well, if you look at the value of the index, right? The value of the index is that number. So I'm going to go and just call the top. I'm going to call the top the index. And so again, a sub 1, 1, a sub 2, 2, a sub 3, 3, a sub 4, 4. And of course, I know that a sub 2 is really -2 and a sub 4 is really -4, but that was handled by the alternating recognition right there. So we'll talk about that in a second. So now from here, let's take a look at what the bottom does. So the bottom, well, that looks like it's linear, right? I mean, it definitely it's growing by a slope of 2. So I know that it's going to be 2n, right? And so from here, if the a sub 1 term is 3, then how do I get to 3 from this 1 here? So if I plug in a 1 right here into n, I'll get a 2, but it would need an additional 1 in order for it to become 3. right? So 2n plus 1, if I plug in a 1, I get a 3. I think that's good. If I plug in a 2 into here, do I get 5? 2 times 2 is 4, plus 1 is 5. I think the pattern's going to hold. 3 times 2 is 6, plus 1 is 7. I think we're pretty good on the bottom. So from here, what that means is that this is going to end up being a sub n equals, looks like the top is going to be the index, so that's going to be n, right, whatever that value of n is, and then the bottom is going to be 2n plus 1, but again, it alternates, right? And so what I'm going to do is I'm going to go ahead and write this down as -1, and since the first term is positive, I'm going to call it n minus 1 here. Because, or n plus 1, it doesn't really matter which one you do. Because if I plug in 1, I'm going to get 0 here. That's going to make this -1 turn to 1, which will be a positive value. So I think that's pretty good. Now, there is another interpretation that I want you guys to all to have, and that is if I started off with the 0th term, if I made this a sub 0 instead, and sometimes it's helpful to see both versions of it. You want to stay flexible because every once in a while it's going to be easy. It's going to be easier and more convenient to start it off from the perspective of the 0th term than the first term. So making sure we're flexible that way is going to be very helpful. So I'm going to do the rest of this in blue. And so if I was to look at this from the perspective of a sub 0, well, then the top really wouldn't be the index. The top would be the index value plus 1, right? Because 0 plus 1, 1 plus 1, 2 plus 1, 3 plus 1. The bottom, his slope is still 2, right? But in this case, if I start from the 0th term, then I'm going to have to add 3 to it each time. And so from here, another interpretation of this would be n plus 1 times -1, in this case, just to the n, over 2n plus 3. And again, it's important to have both versions. Now, on quizzes, I'll only really need one version. But sometimes, and you'll see this a lot on the AP exam, sometimes it's just more useful to see it from the 0th term's perspective. And sometimes it's easier to see it from the first term's perspective. They'll take either one, but we want to make sure that we are being very, very clear as to which version we give to them. So we say, in this case, a sub 0 equals 1/3. And then in this case, a sub 1 equals 1/3. And that is actually a 0, not a 6. I apologize. That's a 0. And that's actually a 0, not a theta. There you go. A filled in 0 for you. And so make sure we're being very clear as to what we're considering the first term to be. So hopefully that makes sense. All right, let's move on to the next topic here. Give me a second here. Let me get some space here. In this next segment, we're going to talk about taking the limit of a sequence. Now, why would we ever want to take the limit of a sequence? It's because sometimes it's really important to know, actually it's not even sometimes, it's oftentimes, it's really important to know what a sequence value is approaching as the n value, as the index value gets super, super large. This will help us determine a lot of things about when we get into series. We'll be able to determine if a sequence is converging towards a value or diverging into infinity. And that will allow us to better get a gauge on whether or not the sum of that sequence is going to be imploding into something that we can calculate or exploding into something that we cannot calculate. And so determining what the terms of a sequence are approaching is really important. And the way we do that is we bust out our good old buddy limits again. And so if I gave you a sequence like a sub n equals n over n plus 1, and I wanted to find out what are the terms slowly but surely becoming as my n's get bigger and bigger and bigger. Well, what I would do is I would really just take the limit as n goes to infinity, right? I'd want to find out the quote unquote infinite term of this sequence. And of course, since we can't plug in infinity, we actually just need to take the limit as n goes to infinity. So if I take the limit of that sequence, and mind you, all limit laws that existed in Calc AB when applied to functions do in fact apply to limits of sequences with the exception of one of them. And I will talk about that very, very soon. In order to find out where this is going, you could just divide both by 1 over n, both top and bottom by 1 over n. We've seen this maneuver happen a lot. So we get 1 over 1 plus 1 over n. As n goes to infinity, we get 1. We probably should have seen that one coming based on the dominant terms of this guy. But what does this mean exactly? What this means is that as my n value gets large, my sequence numbers, my values of the sequence are slowly becoming 1, 1, 1, and 1, dot, 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 slowly but surely becoming closer and closer and closer to that value. And so what we say about this sequence is that the sequence actually converges. So this sequence converges. And that is because our values, our terms, are approaching a defined number or a defined value. Obviously, a sequence would be diverging if we somehow got infinity as our value. And if you look at this example here, I'm sure you can come up with a counter example with an example that would diverge, right? And it wouldn't be too hard to come up with one that did. But we will run into one at some point. And so from here, let's go and just try one more. We'll bring back an old friend here. I'm going to say a sub n is equal to the square root of, say, n squared plus 3n minus n. And I'm going to give you guys a different kind of notation for this. I'm going to bracket it off, and I'm going to say from n equals 1 to infinity. And basically, that's just saying, hey, these are all the terms from 1 to infinity as defined by this sequence generator. So our first step here is I'm going to ask us to define, list the first 5 terms. And then B is going to say, the question is going to be, does the sequence converge or diverge? And so if you want, please feel free to hit the pause button to see if you can do this one on your own. If not, stay with me. I like to go ahead and make my first 5 terms more explicit looking like this. And if you just plug in the stuff, I'm not going to waste a whole lot of time here. This becomes, I'll actually go ahead and do it all in blue. 1, this becomes rad 10 minus 2. This becomes rad 18 minus 3. Rad 28 minus 4, and rad 40 minus 5. First 5 terms, we just listed them. All we did literally is we took 1 and we plugged it in. We took 2, we plugged it in. We took 3 and 4 and 5 and plugged them in respectively and got those numbers. So hopefully that makes sense. But in order to find out whether or not the sequence is converging or diverging, I'm going to want to take the limit as n goes to infinity of the square root of n squared plus 3n minus n here. Now, the way I'm going to reconcile this is I'm going to go ahead and multiply by the conjugate of the top and bottom. So what I get here is I get these guys to multiply. So I get n squared plus 3n minus n squared over the square root of n squared plus 3n plus n, and don't forget, the limit has not been taken yet. Those guys cancel, and so what I get here is I get the limit as n goes to infinity of 3n over rad n squared plus 3n. Now, again, I told you guys that there is one limit rule that does not apply to sequences, and that is our good old buddy L'Hopital's rule. And L'Hopital's rule does not apply to this because this is a sequence and not a function, right? L'Hopital's rule is reserved for functions because that was the ratio of their derivatives, their slopes. And so since a sequence is just a bunch of discrete terms, it's not a continuous function, so it's not going to have a derivative or a slope that I can find. And so what I'm going to do instead, and even if I actually had L'Hopital's rule in this case, I wouldn't do it. I would do our good old buddy, this guy. And I hope you remember this because that is that's a pretty big thing. Limit as n goes to infinity of 3n over absolute value of n over rad 1 plus 3 over n. So as n goes to infinity, I get 3 up top. This guy goes to, oops, and I totally forgot about this guy, plus n over n. Almost forgot about him. This guy will go to 1. And so what I end up with is 3 over 2 as my terms. And so again, my terms are slowly but surely becoming 3 over 2, 3 over 2, 3 over 2. So what this thing does is we can say this sequence converges. The sequence converges. So branching off of limits of sequences, This allows us to find out whether or not a sequence is strictly increasing or strictly decreasing. And the basic premise behind this notion here is that if my next term, or a sub 1, is bigger than my current term, a sub n, right, then what I have is I have a strictly increasing sequence. If my next term is smaller than my current term, then I have a strictly decreasing sequence. And so from here, how do we manifest this? We basically want to be able to prove this idea. The way we do it is within a couple of different ways. It depends on the type of sequence that they give to you, but you have to kind of adjust your strategy depending on what they give you. So for example, if I give you something that looks like this, a sub n equals n over n squared plus 1. Sometimes the most direct approach is the best, where if you said, look, if I have a sub n plus 1, if its relationship to a sub n, if it's bigger or smaller, right, then that'll tell me whether or not I'm increasing or decreasing. But what I tend to do here is I actually tend to subtract. I subtract the a sub n from both sides of this statement here, and I find out its relationship to the number 0. And hopefully this makes sense, that if my result is positive, right? In other words, if my test yields something greater than 0, that means that I'm strictly increasing. If my result is negative, then that means that I'm strictly decreasing on this sequence. So I'm going to go ahead and do that. I'm going to apply this idea to this sequence here. So the n plus 1th term is going to be n plus 1, right? I just replaced the n with an n plus 1, the next term. And I'm going to get n plus 1 squared, not n squared anymore, right? Because this is my next term. And I'm going to subtract my current term from it. So what I'm going to do now is I'm going to go ahead and find a common denominator. And the common denominator really is going to be these two guys being multiplied together. So what I have to do is I have to multiply this top guy by an n squared plus 1. And this guy is going to get multiplied by an n plus 1 squared plus 1. And after a bunch of mumbo jumbo, what I'm going to get is I'm going to get n cubed plus n squared plus n plus 1 minus, looks like n parentheses, n plus 1 squared plus 1. Now from here, so what did I do? How did I get that? I multiplied the numerators together. Now, of course, the denominators are getting multiplied together also, but because the denominators are now common, they don't matter anymore. So I got rid of the denominators in that step. Hopefully that makes sense. I'm going to clean them up a little bit. I'm going to say n cubed plus n squared plus n plus 1. After multiplying all of this stuff out and distributing the negative, I'm going to get negative n cubed minus 2n squared minus 2n. And that's all equal to 0. Again, this step became down here by multiplying this out, multiplying a negative n in. So the n cubes are going to cancel. Looks like I'm going to kind of cancel out the n squared. I'm going to get negative n squared. Looks like minus n plus 1. And now what I'm going to do is I'm going to go and just let n equal 0, let n equal 1, 2, and dot, dot, dot. And what we're going to find is that if I let n equal, say, 1, right, if I was to let say, n equal 2 and 3, this thing would be less than 0. And so what I can determine now is that because this guy eventually becomes less than 0, right, and then as n gets super, super large, I get a very big negative number, which is always going to be less than 0, this guy is going to be strictly decreasing. So hopefully that makes sense. The direct approach can be a little bit off-putting because you end up plugging in n plus 1s into the function. You do have to do it sometimes, but there are a couple more tools that I do want to show you that might be a little bit more straightforward for you. So I'm going to look at the exact same function. I'm going to say, all right, so a sub n is equal to, once again, n over n squared plus 1. Well, at the beginning of the video, I talked about how sometimes we compare these sequences to functions, and I'm going to do that right now. I'm going to go ahead and compare this to f of x equals, whoops, not n, but x over x squared plus 1. And so because I can't take the derivative of this, right, because it's not actually a function, it's a sequence, I can take the derivative of this, and by comparison, I can compare the function to the sequence. And if I could find out where the function is continuously decreasing, hopefully it makes sense that by comparison, if the function is continuously decreasing, then the individual parts would be decreasing in tandem. So I'm going to go ahead and find our derivative here. So f prime of x is equal to low d high minus high d low and square the bottom, and away we go. So x squared plus 1 squared. So let's go ahead and simplify this dude out. I've got x squared plus 1 minus 2x squared. So I'm going to get 1 minus x squared on, over x squared plus 1 squared. And that is f prime of x. Now, if I'm going to find out where this function is decreasing or increasing, right, the first derivative was necessary, but now I'm going to plug this into the sign chart. We know that our critical numbers are -1 and +1. The bottom doesn't produce anything because of he's always being positive. And I'll go and do my sign chart normally because that's just kind of how I rhythmically do it. We got an upside down parabola. The signs are minus, plus, minus. But again, nothing here exists because we're not talking about any kind of negative values that we're plugging into our sequence. But I can say that f is decreasing on the interval from -1 to infinity. So that means that by comparison, I can say, therefore, a sub n decreases for all n greater than or equal to 1. And so that derivative test is what we call this thing. The derivative test can also be used to show strictly increasing or strictly decreasing behavior. Okay, let me get some more space. I'll be right back. Every once in a while, you'll run into a sequence generator that does this. And so it's exponential over factorial. And so when it comes to factorial, you're going to want to get comfortable with this pretty quickly. Factorial operations happen somewhat regularly in sequences and series. And so I feel like this is a good way to kind of get us into the idea of how to appropriately deal with a factorial. So from here, I mean, I don't know if I want to subtract these two. And sometimes comparing factorials, one versus the other, is actually quite obvious. And when that happens, please feel free to go for a direct comparison, the way we did with the a sub n plus 1 minus a sub n. Obviously, I don't think we can derive this. I don't really understand and I don't believe there is one, a derivative for x factorial. And so from here, instead, an appropriate way to perceive factorial is to look at it from this perspective. If a sub n plus 1 divided by a sub n, in other words, the next term divided by the current term. So very similar to how we took on the a sub n plus 1 minus a sub n, we established a relationship with 0. Now in this case, there's nothing we can divide to make it become 0. So what we do is we divide these guys and we try to figure out the relationship to 1. And in this case, we know that if we have a sub n plus 1 over a sub n, if it was less than 1, versus a sub n plus 1 over a sub n is greater than 1, well, if we cross multiply this thing over, and we can cross multiply it over because in this case, all terms are considered positive, right? So there's no risk of flipping the inequality. We can say then that a sub n plus 1 is less than a sub n, meaning we have a strictly decreasing sequence, and then a sub n plus 1 would then be greater than a sub n. In this case, if we had a ratio that was greater than 1, which would be a strictly increasing sequence. So it's good to know how to divide out factorials. Again, like I said, we're going to do it somewhat often. So I'm going to go ahead and apply that idea to this problem here. So I'm going to say 10 to the n plus 1 over n plus 1 factorial. And I'm going to divide that by 10 to the n over n factorial. Now, I love four-layered fractions because that gives me 10 to the n plus 1 over n plus 1 factorial times n factorial over 10 to the n. Now, if you're thinking, wait a second, this is making my life worse. How do I deal with this? Well, we can actually deal with the exponents pretty easily. Because back in logistic growth and exponential growth, we learned that when we have two exponents being added together, we can separate them out. Whoops, that's a 0, not a weird-looking D. like that, which will allow for the 10 to the n's to cancel quite appropriately. The question is with the factorial. Well, the factorial is a bit different. Hopefully it makes sense that the way a factorial works, right? If I had, say, like 10 factorial, it would be equal to 10 times 9 times 8 times 7 times 6, dot, 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 right? So how do I get each term? Well, if I called this guy n, that means that the next term would be n minus 1. The next term would be n minus 2, n minus 3, and so on and so forth. So what that means is that I'm multiplying by the next succeeding number down from where I'm at. Which means that if n plus 1 is my first number, that means that n is my next number. And then n minus 1 is my next number after that. And actually, n minus 2 and n minus 3 and dot, 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 right? Well, the way I can actually solidify this and make him a little more palatable is I can call him n plus 1 times n factorial, right? And then that n factorial can cancel out with this n factorial here. These 10 to the n's can cancel, leaving me with 10 over n plus 1. And now what I want to do is I want to look at his relationship with the number 1. And so notice how it's going to be larger than 1 up until a particular number. And I would encourage you just pause real quick and just say, hey, look, do I know what that number is? So if you look at this number really, really hard, what is the number that's going to make this thing suddenly start decreasing? And if you guessed if n was greater than 9, right, then we would be decreasing. You would be correct, because if n was bigger than 9, we'd have 10, right? And then 10 plus 1 would be 11. So 10 over 11 would be smaller than 1. So if n is greater than 9, then a sub n decreases. And what happens is that it decreases for the rest of its life. So sometimes you'll see books call this eventually strictly decreasing. Eventually strictly decreasing. And that's fine. As long as and this book defines it as if you eventually strictly decrease, you're strictly decreasing, which makes absolute sense. And so, yeah, that will do it for this part right here. I'm going to go ahead and come back with a couple of examples. Give me a second. So here we are with 3 examples of different types of sequences. And of course, the question always comes up, which test should I use to figure out whether or not the sequence is converging? Well, I hate to go back to my original mantra from integration by parts, but basically it boils down to just don't make the problem worse. And so you go with whatever test seems to make sense to you. Of course, this first one, you could use the next term minus the current term, or is the next term bigger than the current term? I will very likely use the derivative on this one because this looks like a function that's easy to derive. So first thing I'm going to do is I'm going to let f of x equal the functional version of this, which means f prime of x is equal to 3x squared minus 8x. And if I factor out an x, I'm going to get 3x minus 8, which makes my critical numbers at 0 and 8/3. Again, I chose the derivative because it looks easy to derive, and the calc AB in me is leaning towards that. So I'm going to go 0, 8/3. So now from here, if I look at this as an upward-facing parabola, then it means I've got plus, minus, plus in my sign chart. But of course, again, nothing here exists. And we hopefully do know that. And so we know that f is increasing on x being greater than or equal to 8/3. But of course, we can't say that for n, right? Because n is only plugging in whole numbers only. So I'm going to go ahead and say that n is strictly increasing on n is greater than or equal to 3, because 3 is the next number, right? 3 would be right here. 3 is the next number that would allow the increase to happen. You could also say n is greater than 2, because 2 would then imply that you are picking 3 as long as you didn't include the equal to sign. And so it's entirely up to you on how you want to present that as your answer. Number 2, again, actually, it wouldn't be wrong to use the derivative test on this one. Nothing wrong with that because it's a pretty easy quotient rule. But instead, because I want to show you the n plus 1 version of this thing, let's go with n plus 1 over n plus 2 minus n over n plus 1. And then after finding some common denominators and stuff like here, you will get 1 over n plus 2 times n plus 1. And of course, because our n's are always positive, right? Again, in the sequence, we only plug in the whole real numbers here. This is going to be greater than 0 at all times. So this guy is strictly increasing for all n greater than or equal to 1. And then, of course, our good old buddy factorial. I'm not going to derive this thing. I'm not going to compare this thing, although there might be merit to comparing it if you wanted to. And so I just feel like it makes more sense to me if I ratioize it. So I'm going to say 2 to the n plus 1 over, and I got to be careful here. This is going to be 2 parentheses n plus 1 like that, all factorialized, divided by 2n factorial over 2 to the n. And again, I just think this idea of being able to cancel out factorials is going to be really helpful here. And so we got 2n factorial over 2 to the n. So again, I've got 2 to the n times 2 over, this is going to become 2n plus 2 times 2n plus 1 times 2n factorial over 2n factorial over 2 to the n. The factorials cancel each other. The 2 to the n's cancel each other. So I have 2 over 2n plus 2 times 2n plus 1. And of course, if I compare this to 1, if I plug in the lowest thing that I can, which is going to be even 0, right, I would get equal to 1. But if I plugged in 1, right, this thing would be less than 1, which means this is going to be strictly decreasing. So hopefully that makes sense. Welcome to the introduction to sequences. And in the next section, we will move on to how these sequences, how they become convergent or divergent, depending on when we add them all together, when we get to the infinite series. So hopefully this makes sense. As always, please leave comments or questions in the comments area. I will see you all in the next episode.